Hello everybody. I've been trying for the last few days to complete this video. Hopefully we won't have any glitches now. What I've been wanting to do is cover what you should expect about the final, but also just talk about the course in general. It's been a fun experience for me, and I noticed that there was a lot of resistance, especially initially, to the amount of work that had to be done. And that's okay, because that's part of being a statistics professor. You're always going to have a lot of resistance. People resist because often you feel that the work is nonsensical, if you don't mind me using that term. And I understand that, because you believe that in the real world we never have to do calculations. What's the point of it? My point in doing it is having you to really understand what is behind the work you're doing. Of course, like for instance, when you drive a car, it's not important to know how the car works, what are the mechanisms to allow the fuel injection, etc. system to work, but knowing how something works actually permits you to better understand when you run into issues, to better understand, especially when it comes to statistics, and when you're supposed to be an expert in the field, to be able to deliver the message to your constituents. If you're not a mechanic, that's your choice. But if you're studying, getting your doctorate in nursing, and you're expected to be able to understand and to explain the results of different studies that you're going to be either using in your arguments for some intervention, I'd expect you to be able to really explain what's going on. That doesn't mean that you have to do the equations for people by hand, but what it means is that you have to be able to deliver the message and explain what is significance and what is not significance, and be able to back up your argument confidently. And to do that, you really need to understand what's going on behind the work you're doing. Some of the stuff that we did this semester, like power analysis and sample size calculations, are essential, especially if you're planning to do any kind of studies, or you're planning to write for a grant, a grant application for anything, for funds to conduct studies, for funds to implement an intervention of some sort, or even funds just to open a new center of some sort. You have to prove that you can achieve what you say you intend to do, and for that, the easiest way to do that is to identify the power, and it studies the sample size that you need. So there's a lot of reality to what we did. So in terms of the types of questions you can expect in the exam, really what we're looking at is your ability to answer some of the more basic, more fundamental questions that allow you to interpret results well. For instance, positive predictive value. That's something that we talked about and we assessed. PPV is the probability of an individual having a disease given that one tests positive for the disease. So that there's a lot of practicality to that measure. You can see my internet is having some issues here. That's unfortunate. I'm at home. I'm not at work today. But, there's just some little glitches here and there. But, as long as you get the message, that's what's important. And my temptation is it's not an internet issue. It's more of just a regular program. So understand how you calculate the PPV, for instance. Understand what sensitivity and specificity and how those are related to PPV. You should be able to, if asked, you should be able to, just knowing the prevalence, the sensitivity and specificity, and perhaps the population size, be able to calculate positive predictive validity. If you have the samples, if you have the population size, you can create one of those kind of tables, 2x2 table. If you don't have a population size, you just use this Bayes' theorem. So that assumes that you understand a little bit about probability, because we did talk a lot about probability, especially earlier in the semester. Please make sure you understand p-values and what p-values mean. P-values are the probability of the observed result given that the null hypothesis is true. It assumes also that you know what the null hypothesis is and the alternative hypothesis, or what that means and how they're structured. Understand how to calculate power and sample size, as I just mentioned. You have all the formulas for that. But you should really deeply understand what power means. Power is the ability to reject a false null hypothesis. Understand what alpha is. Alpha is the probability of a false positive result or a type 1 error, and how that's related to power. And let's see, type 2 error, probability of failing to reject a false null hypothesis, which is really not a good thing. That's really bad. That's the opposite of power. 1 minus power is equal to beta. 1 minus beta is equal to power. So 1 minus the false positive result. It is your power, right? Oh, no, not false positive, excuse me. 1 minus your beta, your type 2 error, is your power. So let's see what else. Let's see. Okay, so we talked about that. Regression analysis. Please be able to conduct, especially to understand what a regression analysis is and how to interpret the results. Remember the little bees that you see, not the buzzing bee type bees, but the bees in the regression equation. So are slopes, right, or intercepts. So any regression equation basically looks like this. You can visualize this. You have a y, right, with a hat on it. When there's a hat on it, it means it's an estimate of the population, right, value. Or really, it's an estimation of an individual score on whatever your dependent variable is. And I say population value because we're always trying to make inferences about the population, right? The y hat is different than the y itself. The y is the actual observed value on whatever the dependent variable is. The y hat is the predicted value. So we know the residual is the difference between the two. That's the error. But when we're doing the y hat equation, we're not including the error because it's just an estimate. But then we have that equal to the intercept value, where the regression line would cross the y-axis. So usually that's b sub 0, and to that we add whatever the predictor variables are in the model, and each of those predictor variables comes with a slope value. That's like a b sub 1 for the first variable, it's called x1, and then we might add b sub 2, which is the slope for the second variable, and so on and so on. When we have just one predictor, we have simple regression. When we have more than one predictor, we have multiple regression. You should be able to calculate those b values. You can calculate the b value, the slopes, from the correlation. Okay, as long as we have the means and standard deviations of predictor and outcome variable, you can also calculate the intercept value. So you can do all that by hand, and you'll probably be asked to do that. So how do you interpret these? So when we're talking about a specific predictor variable, we say that each unit increase in the predictor variable, well, you can do this whether or not the slope is significant, but if it's not significant, it's worthless to interpret it. But we say each unit increase in your independent variables associated with a b increase or decrease in your outcome variable. And if the increase if the b is positive, it's a decrease if it's negative. So just make sure you can interpret the results of a regression analysis pretty well. Now, regression analysis, as you know, is associated with an f value for the overall model. It's an f statistic, and it's also associated with a t value for each of the slopes. In general, we're interested in those t values when it comes to regression. We just want to know whether or not each of our predictors is significant. Oh, by the way, when you talk about predictor, you always have to say holding all other variables constant. Okay, so like if I'm trying to predict smoking from number of peers who smoke, I'd say each peer who smokes, each increase in the number of peers, or each additional peer who smokes, is associated with a b sub 1, with this first variable, increase in smoking, right, if it's positive, holding all other variables constant. You always want to add holding all other variables constant. F-tests, though, are used for analysis of variance, which is another topic that we covered. We talked about ANOVAs, right? An ANOVA, analysis of variance, is used when we have more than 2 levels of our independent variable. Now, you can use it with 2 levels, that's fine. But we generally use it when there's more than 2 levels of an independent variable. Sometimes we also use it when we have more than 1 independent variable. Let's say if we only have 1 independent variable, we have a one-way ANOVA. If we have 2 independent variables, say I'm looking at the effects of a new experiment, so I have an experimental versus a control group on some disease, and when I do that, I might want to add another independent variable, something like person's sex. So now I have 2 independent variables. It'll be a 2-way ANOVA. Each of those independent variables, say, has 2 levels. So with experiment, we have experiment versus control. Sex, we have male versus female. That would be actually a 2-by-2 ANOVA. If our experiment or independent variable has 3 levels, like say low or high dose versus placebo, and then the other independent variable is sex, we have a 2-by-3 ANOVA. It's still a 2-way ANOVA, right? But one variable has 2 levels, the other has 3, so it's 2-by-3 ANOVA. That would actually create 6 cells that we have to fill in with data, right? And that's one of the problems you have with ANOVAs. You can get too many cells and not enough participants. Another issue with ANOVA, especially when we have many different levels of our independent variable, is that ANOVA is an omnibus test, and it just tests the overall effect. Right? Is there a significant difference somewhere among the different groups? Well, the problem is that while that's interesting, we want to know where specifically those differences are. So we start testing for differences among different groups. So is it group A, say there's 3 groups, is it group 1 versus group 2 that's different, group 1 versus group 3 that's different, or group 2 versus group 3 that's different? The more tests we do, the more likely we're to commit a type 1 error and get a false positive result. Our alpha is the probability of a type 1 error. So the more tests we do, the more likely we're to commit a type 1 error. There's going to be some inflation there. Okay, some inflation, so you have to be careful about that. So you want to look at family-wise error rate and be able to calculate the inflation. Also, we can protect against that by using any number of any types of methods that are available. One of them is the Bonferroni correction, where you just take your alpha value, whatever your selected alpha is, and divide it by the number of tests you're going to do. So then each test will be judged on that new alpha value, where the total of all tests will equal the original alpha. So if you have 3 tests and you divide alpha 0.05 divided by 3, each test will be set at that new alpha level. However, overall, if you divide it by 3, the 3 tests will have an alpha of 0.05. So make sure you can do that. Make sure you can note how many tests are being done, or how many possible tests are being done, using that choose function, if you remember that, also known as the binomial coefficient, right? That'll give you the amount of ways one could, say, choose 2 tests at two levels at a time, right? Compare them out of how many possible tests there are. Let's see. What else? Groups there are, or levels of your independent variable, I should say. Speaking of binomials, you should be able to predict the number of successes you would have using the binomial function. See, be able to calculate confidence intervals. There's many different types of confidence intervals. Odds ratios and relative risk. Both of those come with chi-square, being able to do chi-square, of course. So the last test that we did, one of my favorites. And in general, just make sure you understand what you need to know to be successful, which is, especially in interpreting results, which is being able to assess whether or not a result is significant using p-values or critical values. Oh, and then something like perhaps calculating somebody's percentile rank. That would be important to you. Using the z-score. Well, that's pretty much all that I want to do now. Hopefully this video will finally work. So I want to thank you again for a wonderful semester. You guys really challenged me a lot, and hopefully I challenged you a lot, and hopefully you feel that you're better for it. And again, I know that statistics isn't everybody's favorite, isn't everybody's cup of tea, but if it's not, drink coffee instead. Alright, have a Merry Christmas, and I'll contact you again. Thank you.